Every once in a while, a revolutionary product or initiative comes along that changes everything. At Halliburton, we have been very fortunate to have introduced many of these. In 1919, we executed the first cement job and transformed how the industry approaches wellbore integrity. In 1922, we developed a two-plug system for rig efficiency and optimum displacement. In the 2000s, we introduced both iSem and WellLife, two revolutionary software solutions to model the entire life of the well, from planning to placement all the way to abandonment. And the list goes on and on. My name is Walmi Cuello Jimenez. I'm a product champion for cementing software. And today I will introduce you not to one, not two, not three, but actually 6 great solutions that encompass iTOC. Instantaneous topo cement, a revolutionary initiative that enables for real-time barrier placement, real-time monitoring, and ultimately instantaneous validation. It is important to highlight that when we take a look at cementing operations, we can divide it in 3 key phases. Number 1 is the design and the tailoring phase. Number 2 is the execution phase. And number 3 is the validation phase. Historically, a lot of attention is placed on identifying different risks and building mitigation plans during the design and the tailoring phase, so that execution is as close to the plan as possible. And then typically, the validation phase takes place anywhere from 12 to 72 hours after execution, or in some cases even longer, where issues or challenges take place during placement. As a result, at Halliburton, we are focused on instantaneous validation, the ability to assess real-time and forecasted fluid positions while the job is being executed. All of this to the point that a topo cement validation report can be provided to you as our clients right after the job is placed. This will give you the opportunity to use this information in order to meet regulatory requirements. Now let's take a look at these 6 solutions that encompass iTOC. Number 1 is real-time validation. This solution gives you the ability to monitor job placement and inspect the downhole ECDs while execution is taking place. Number 2 is Real-Time Advisor, a solution that gives you the ability to forecast job placement while the job is being executed, and most importantly, it can give you the opportunity to adjust placement parameters in an attempt to meet job requirements in order to achieve topo cement. Then we have SemLife, a cloud interface that will enable you access to real-time job execution or historical job results. Then we have Low Circulation Wizard, which merges our optimized understanding of the impact of multiple loss types on hydraulic response of the wellbore, and as a result, the impact of losses on topo cement. The 5th solution is CVL Visualizer, a solution that will give you the ability to compare side by side the accuracy of our 3D model along with actual CVLs. In addition, this will serve as an opportunity for us to continue to push the boundaries of our 3D model predictions, and likely will serve you as a topo cement confirmation to meet regulatory requirements. And finally, we have temperature mapping, a solution that enables for monitoring of cement hydration while waiting on cement, and thus enable you for Strally placement and topo cement assessment. This will give you the ability to measure fluid placement and assess topo cement potentially even prior waiting on cement time based on lab testing is achieved. This will enable you in some cases some additional savings from your operations, giving you the ability to resume drilling at a much faster pace. And ultimately, this measurement of fluid placement as a result of temperature evolution due to hydration can be used as a measurement of cement position or cement topo cement in order to meet regulatory requirements. Now let's dive into the first solution. The real-time validation is a solution that gives us the ability to assess execution deviations from the design or from the planning. All of these while execution is taking place. This will also enable us to monitor fluid positions while the job is taking place, and naturally, what is the end of job fluid position. You will have access to the main 4 variables. In real-time pressure, real-time slurry rate, real-time density, and real-time slurry volume, in addition to having access to the calculating pumping pressure. The calculating pumping pressure is calculated by the model, geometry, fluid properties, and all the different placement parameters and pump schedules that are defined in the model by taking into consideration the actual real-time rate and real-time density. When there's an optimum match in between the calculated pressure and the real-time pressure, especially during the displacement phase, we can conclude that the hydraulic response of the model matches the hydraulic response of the wellbore. And as a result, the actual calculated ECD is representative of the downhole ECD that the wellbore is exposed to. We can also have a comparison between the design ECD and the calculated ECD. And again, when there's a hydraulic equivalent that the model has compared to that of the well, then this downhole ECD or calculated ECD is representative of that of the well. And also importantly is to have access to the 2D fluid position. This access is provided by the system while the job is being executed and also at the end of the job. Now let's take a look at a demo of how this solution is implemented. So what you can see here is on the top left, you have a real-time job summary plot. We will have pressure, density, flow rate, and volumes, and we'll have time in the y-axis. In the real-time ECD, initially we have what is the design or the plan ECD expected for this job. And once calculations or the job commences, you'll start seeing what is the calculated or the expected downhole ECDs. And then we also have the 2D fluid positions, where we'll show what is the position of the fluids while the job is being executed and at the end of execution. So initially in this case, what we're doing is placing the lead cement. What you can see here is that you have the volume increasing as you continue to pump. You have a flow rate in the order of 4 all the way to 5.5, 6 bars per minute, and the density is roughly 11.8 ppgs. As you can see, initially there's a fairly good match in between the calculated pressure, which is the dotted red line, and the solid red line, which is the real-time pressure. Initially, there's no major discrepancies between the calculated ECD and the design ECD, which is a good representation that the model is providing a good hydraulic response or an optimal hydraulic response at this point. As you can see at this point, rate has been reduced to 0 and there's no additional volume being pumped. What the crew is doing at this point is increasing density and getting ready to commence placing the tail. The tail density is around 15.8 ppg, so when that's a stable density for the tail is achieved, the rate will continue to increase or will start to increase, and then the placement of the tail will start. That will be roughly at stage 3. So what you can see here that the fluid position is showing the actual free fall that is predicted by the model, and it shows how the lead or this fluid is displaced in the wellbore fluid in this case. Once we reach stage 3, which is the point at which the tail will commence pumping, you'll see the rate increasing at a rate of roughly 3 barrels per minute, and you can start seeing the tail being placed into the casing, or into the well ultimately. You can see the pressure response from pumping the tail already starting to be apparent or indicated by the model, as well as the volume continues to increase as initial volume of tail is pumping to the wellbore. There was no pressure response while there was the crew was increasing the density, since no fluid was pumping to the wellbore. Fast forward in the placement of the tails cement, you can see that this is a fairly large stage considering the lower rate that is considered for this job, which is roughly 3 barrels per minute. We go until we reach the point that rate is reduced to 0, meaning no additional volume of tail will be placed at this point, and the crew will proceed to wash up the lines. There's no additional fluid going into the wellbore. This extra fluid will be diverted into a pit. And then in stage 4, prior to stage 4, the crew is gonna drop the top block, and after that will commence the displacement phase. So as you can see, the rate will commence increasing in the order of roughly 6 barrels per minute. The density of that displacement mud or water-based mud is roughly 9.4 barrels ppg, or pounds per gallon. You can see how the volume starts to increase. There's good correlation between the calculated and the surface and the real-time pressure at this stage. We're not lifting fluids at this stage yet. The lead has not reached the bottom of the well. One of the advantages of this tool is that will give you the ability to assess at any given time where your fluids are, and if there's any issues that arise during the execution, you will be able to have an idea of what the fluid position is at the moment of the issue occurring. We'll fast forward the displacement phase, which is one of the most critical phases in order to prevent any potential losses or any potential changes, or keeping the ECD within the pore pressure and the fracture gradient. What you can see here is that there's a good alignment towards the end of the displacement phase, or the last quarter of the displacement phase, in between the calculated and the real-time pressure. This good match between the maximum pressure and the final circulating pressure, or the bump pressure, indicates that the hydraulic response of the model matches the hydraulic response of the well. And as a result, the ECD that is obtained for this case is in fact the downhole ECD that the well was subjected to. This is information that you can use in real time in order to determine whether a well is going to be, whether a zone is going to be fractured or not. Also, whether that ECD is maintained within the pore pressure and fracture gradient limits. And in addition to that, and also importantly, is to determine which actual ECD was the well exposed to, so that you can use that information for adjacent wells or future wells. But the important part of this tool, or this real-time validation, is, in addition to having access to that 2D fluid position. This is important in cases where there are some issues that take place while executing in the middle of the job, but also important to give you an accurate representation, or an optimal representation of where the fluid positions is at the end of the job, meaning what are the top of the cements, especially when there's an optimal match in between the calculated pressure and the real-time pressure. So it's important to know that the real-time validation tool will give you the ability to monitor placement while job is being executed. You're able to assess the 4 key variables in pressure, rate, density, and volume. In addition to that, if there's a good hydraulic response of the model compared to that of the well, there's a match, then you will be able to also measure or monitor ECDs in real time. And most importantly, you'll be able to have an idea of 2D fluid position while execution, and 2D fluid positions at the end of the job. The real-time advisor tool pushes the boundary of real-time validation, the previous solution, mainly by enabling and giving you the ability to have a better understanding of whether the job objectives are to be met or not. All of these while you are executing the placement process. What does that mean? What it means is that while you're executing the job, real-time validation focuses on from the beginning to the present point in time where you are during the placement. But the real-time advisor will forecast what that type of cement is. From any point while executing the job, it will give you the ability to understand whether that type of cement objective will be met or not by displaying a forecasted type of cement, a forecasted surface pressure, and a forecasted ECD. In addition, this solution will enable the cementing operator or the engineer on location to adjust multiple controls in order to tailor job placement with the end in mind of achieving operational success and ultimately achieving top of cement. Among those controls, we have open hole access, loss depth, and we're also considering adding friction correlations and also evaluating surface lines. What this means is while job is being executed and in the midst of execution, the operator or the engineer will be able to monitor or to change what is the annular axis in order to get a better hydraulic match of the model or the prediction of the model compared to the actual real-time response of the well. Adjust or add a loss depth in case the losses are attained during execution, just so that we are able to attain a better hydraulic match while executing the job, and potentially adding or changing friction correlations and surface line correlations as well. What this will do is give the operator and the engineer location the ability to adjust these controls in order to improve the hydraulic match of the prediction so that the hydraulic response of the well is simulated accurately or with higher accuracy. As a result, the forecast will be able to give the operator and the engineer valuable information to make well-informed decisions while execution is taking place. You'll be able to adjust these controls in order to maximize the probability of achieving the goal and to achieving operational success and ultimately meeting those top of cement requirements. Now let's take a look at a demo for this tool. So what we have here is the 4 controls that we mentioned earlier, which is open hole access, loss depth, friction correlations, and surface pressure. This is a preliminary proof of concept that we have for this tool. This is not the final user interface that you'll be exposed to, but it's representative of the capabilities of the tool. In the top graph, you have pressure versus volume, which could be pressure versus time. This is pump volume. In the bottom graph, you have ECD, equivalent circulating density, versus volume with the pore pressure and the fracture gradient limits. Dotted line represents the projection. What is the surface pressure projection? Should everything go as per plan without having to start in the job. These markers highlighted in red represents what are the plan or the design markets. What is the plan volume? At which point in time are we expected to pump each specific stage? And these dotted black lines represent the real-time markets. They initially match the design markers because we have not executed any stages yet. Then in the bottom graph, you have the calculated or the forecasted ECD. Basically, what is the expected ECD that we're going to achieve should everything go as per plan. Then on the right side, we have the 2D fluid position. We have measured depth in the y-axis and diameter in the x-axis, with these black lines representing the actual casing size and the blue fluid the blue color representing MAD, which is present in the wellbore prior to executing the cement job. Initially, the projected top of cement matches the design top of cement. We're monitoring in regards to this specific demo, the tail top of cement. So the projection is going to be focusing on the tail top of cement, and there's also a design lead top of cement. Since nothing has changed, the job is not executed yet. The projected top of cement matches that of the design. If there's any deviations between design and actual, we should see a response or a change in what that projection is for top of cement, in addition to a change and response to what that forecast is for either surface pressure or ECDs. Now let's take a look at the demo for real-time advisor. Now let's walk back and let's make sure that we go through the demo. So the initial stage what we have is spacer. So we're pumping the spacer into the well. That's stage one. There's no major changes on plan compared to actual execution. So what you can see here is that you have a calculated pumping pressure, which is the orange yellowish line. You have a real-time pressure, which is the green line. There's no major discrepancies between the two. We have a good match. We have used our control one, which is the open hole access during the pre-job circulation phase, in order to generate a good match between the calculated and the real-time pressure. That means that the geometry is providing an optimum hydraulic response for the model, which is representative of the well. There's no major changes on rates and volumes. As a result, there's no changes on the actual stage tickers or markers in real time versus the stage tickers or markers for the design phase. Then we finish pumping the spacer and we commence pumping the lead cement, which is stage 2. Again, there's no major changes, no major discrepancies. Something else to note here is that the projected top of cement is overlapping the design top of cement. The design top of cement is in the back in the blue color, also represented here by the marker. There's no discrepancies or major discrepancies in regards to rates and volume while pumping the lead cement, and then we proceed to place the tail cement. Again, no major discrepancy towards the middle of the job. However, towards the end of the job, something we can point out here is that you see how the red marker for stage 4 is not in alignment with the dotted black line for stage 4. Keep in mind that the dotted black line represents the actual. What this means is that you pump for longer time. That means that you pump more volume, keeping the rates more or less constant. If we pump more volume and the geometry hasn't changed, we have not attained losses, we should see a response on the top of cement. That means that our projection, since we pump more tail cement, is indicating that the projected top of cement for that tail is going to be at a shallower depth. It's going to be at a higher point. We're still meeting the objectives, so this is of no concern to our operations up to this point. We go to a stage 4, which in stage 4 basically start displacing with water. We drop our top plug, we displace the top plug with water, about 5 to 10 barrels of water. And then we go to stage 5, which is the displacement stage. Displacement stage, we monitor how close our calculator or our prediction for the calculated pumping pressure calculated based on the model versus the real time is. It's a good alignment between the two. So far we have a good match. We have a good hydraulic response of the model compared to that of the well. As we get to 3/4 of the displacement phase, something we note is, and the advantages of this application and this solution is that we'll give the operator this forecasted information that will enable the engineer or the operator on location to make well-informed decisions. Just to give you an example, in this case, you should be able to see that the ECVs is close to the limits. As a result, the operator is advised to reduce the rate or have the ability to reduce the rate, which is precisely what this operator does. By reducing the rate, you control or minimize the ability or the risk of fracking that specific zone. Still no major impacts to the operation, you still have good alignment between calculated and real-time pressures. Your top of cement projection has not changed, you still have there's no losses, there's no indication for losses at this stage in time. Your projected top of cement is expected to meet the requirements. In fact, is projected to be slightly at a shallower depth compared to what the requirement is. Okay, and at the end of the job, we're able to actually establish that the final placement of the fluid is as indicated in the 2D fluid position graph. The projected top cement is at a shallower depth compared to that of the design top cement. The objectives were met. The ECD was kept between the pore pressure and the fracture gradient. The forecasts enabled the operator or the engineer on location to make well-informed decisions. By reducing rates, they were able to minimize the impact of ECDs on potential losses. So in regards to real-time advisor, as this continues or pushes the limits and the boundaries of the real-time validation solution. While the real-time validation focuses on anywhere from the beginning to the job to that present time while execution, and how that calculator or how that hydraulic response is in alignment with the well response. The real-time advisor looks beyond that point. It forecasts what is the expected response or output of the job, taking into account all the changes and variations that had taken place up to that point. And it will give the operator or the engineer on location the information in order to make decisions in real time in pro of achieving operational success, of achieving that top cement goal. That takes us to our third solution, SunLife, which is an easy access cloud-based interface that enables remote monitoring by connecting remote engineers and supervisors to the rig site. And also importantly, will allow you as our clients to have access to real-time execution or real-time jobs that are being executed in addition to having access to some historical job results. In addition to this will also enable access to any subject matter experts on a specific area to monitor any job regardless of where the SME is located, or where, for that matter, or where the rig is located. The advantage of this tool is that it'll give you the ability, especially if you're monitoring or having to manage multiple projects, multiple rigs, and you don't have the ability to be at every rig location at the same time, but all projects are critical to you and important to you as they always are. You'll have the ability with this tool to have access to those jobs while execution is taking place. You'll have the ability to provide access to the specific SMEs that are required to monitor these jobs, regardless of where she or he is located. And that's an easy access. All you'll need for this is a regular internet connection, and there will be no limitations in regards to being connected to the same network as that of the rig. In order to locate those active jobs, one of the views that we'll have on this tool is the map view. So when you'll have access to your area, to your project, to your rigs. And for those jobs that have been executed for your rigs and your area, you'll be able to monitor which ones have been executed and which ones are ongoing. By simply clicking on any of these jobs, each circle represents a specific latitude and longitudinal location of that specific job, of that specific well. Then you will be able to access in real time for those that are ongoing, whether those access those jobs while they're taking place. In addition to that, you'll be able to actually access historical job results. You'll be able to download the real-time data for those that took place in the past, and you'll be able to monitor and observe any jobs that are taking place in real time. You'll have a list view, which is the same information as the map view, just in a tabulated format, or have a specific BIDA ID, which is specific to each job. You have a job name, rig name, well name, which one is the operator, and what is the case that the job is being executed based on. This case name comes from ISO. In regards to the data structure that you'll be able to access, you have all the different data that the operator and the engineer will have access to in location, meaning pressure, fluid densities, rates, volumes. For offshore case, you'll have access to liquid additive rates, etc. In addition to that, you'll have access to calculated variables such as calculated surface pressure, calculated bottom hole ECDs. For those fluid stages, you will be able to assess what is the density histogram of each specific fluid stage. That will give you an idea of if that density KPI is being met or not. This is while the job is being executed. You'll have access to an average density, a planned density, a min and max, and a standard deviation. And also importantly, you'll have access to what is the 2D fluid position while execution is taking place. And also important, what is the 2D fluid position at the end of the job. The main goal of all these tools, as you can see so far, is giving you the ability to access the data in real time, have access to instantaneous topo cement, which is 2D fluid positions while job is being executed, knowing where your fluids are at any given point in time, from the beginning of the job until the end of the job. And SEMLife is just the gate, the interface that will give you access to all of that information. You don't have to wait until the end of the job and then a post-job report evaluation is generated. You're going to have access to this information while execution is taking place. Now, just to give you an idea of what the tool initially looks like, this is just a representation of the data transferring part. In this case, we'll transfer in pumping pressure, slurry rate, slurry density to the tool. And as you can see, you'll have access to all the different stages and events that the operator defines in while executing at the rig site. Same names that the operator defines, so you know what is being done at any given point in time in terms of which fluid is being pumped, etc. And in addition to that, you'll have access or the ability to download a CSV file while the job is taking place, or you can wait until completion of the job in order to access it or to download it. Keep in mind, you'll have access to the historical job that have been already performed. So even though you were not able to monitor any of these jobs, you will be able to go back to SEMLife, click on that job that you want to see that real-time data from, and you'll be able to download it at any given point in time. So the advantage of SEMLife is giving you easy access to real-time data so that you can have access to instantaneous job validation, so that you can have access to, after execution takes place, the ability to provide or print or attain a topo cement validation report, so that you can provide that information or use that information to meet your internal requirements and in some cases potentially regulatory requirements. Our next solution is low circulation wizard. Low circulation wizard optimizes our topo cement prediction by improving our low circulation model. The low circulation wizard consists of two stages. Number one is the model calibration. The model calibration stage consists of employing the geometry, fluids properties, placement parameters, and other factors from the ISEM design file, and combining that with our understanding of what is the loss type, whether that is an induced fracture, a natural fracture, or a permeable formation. What is the loss rate that is typically attained in that specific well or in that specific field? What is the expected loss depth, which typically, or what is the formation that usually results in losses? What is the area that usually results in losses? And by combining all of the input information from ISEM in regards to geometry, fluid properties, placement parameters, etc., and our understanding of the loss scenario, then the model for calibration purposes determines or calculates what is the size of the loss zone. After assessing the size of the loss zone, then the model moves into the next stage, or the second stage, which is model prediction. By combining the size of the loss zone and input into the model what is the fluids system that are going to have an LCM package and an LCM concentration mixed to it, or associated or tailored with it, then the model will be able to assess what is the final loss rate, what is the final loss volume, what is the final pressure at the loss zone, and ultimately what are the top of the fluids. After the fluid LCM package has been pumped through the entire wellbore, and the interaction between the LCM and the fluid package have been evaluated to achieve mitigation of that loss or plugging of that loss zone that is characterized by the loss zone size. So the powerful of this tool is being able to tailor fluid and LCM packages in order to mitigate losses, in order to mitigate or plug a specific loss zone geometry or a loss zone size. By being able to tailor this fluid LCM package, we're able to maximize or improve our topo cement prediction. Now, how we assess the accuracy of this model? What we have done is we have looked at different locations, different basins, different loss types, ranging from including all the ones that we can model, which is natural induced fractures along with permeable formations. But importantly for us to assess a wide range of loss rates, we went from 30 to 240 barrels per hour. In addition to that, also important for us to evaluate different fluid LCM packages in cases where the LCM was added not just to the spacer but also to the cement, and different concentrations. So what we're looking at here is tune defense cement spacers with Bridgemaker 2, more conventional LCMs such as cold seal and polyflake at different concentrations. Other cases where we added LCM, in this case Bridgemaker 2, to the tune defense cement spacer, but also to the lead and the tail at different concentrations. And in other cases where we employ more conventional spacer designs with LCMs, and also adding those LCMs to the cement. Ultimately, what we measure in the actual jobs was what is the percent reduction in losses after the job and after the treatment has been employed, and then what is the prediction of the model. What you can observe here is that the prediction of the model based on the actual tests is at least 90%. When we compare these to other models that are based on literature reviews and other models that are out there, we can assess that typically all the other models are either numerical based on some statistical analysis. Their accuracy is in the order of 66-67%, while our model is physics-based and has an accuracy of at least 90%, which is extremely good. But in addition to being able to assess the accuracy based on actual well results, based on actual case studies and actual data, we also challenge the model in the manner that if our loss prediction is accurate, the hydraulic response of the model when exposed to losses should match the hydraulic response of these cases, of these wells where losses took place and where our accuracy is high. And that's precisely what we check. So when we're looking at here is surface pressure, you have in the yellow-orange line real-time pressure, the hydraulic response of the well, versus calculated pumping pressure, the hydraulic response of the model, by modeling losses, by modeling those specific LCM, fluid and LCM concentration and packages, geometries and distribution. Those tailored fluid solutions, we model those, which is what actually was executed during the jobs. And we assess what is the response of the model. If the model is accurate from the prediction, it should be also accurate by matching these hydraulic responses. And that's what we were able to achieve here. So you can see there's no major discrepancies between the real-time pressure and the calculated pressure. In addition to that, we're able to assess what is the rate in, the rate out while executing these jobs. And by doing so, we're able to determine at which point in time or which point during the placement process we actually cure the losses. or mitigate the losses, depending on the case. In terms of the outputs that we're able to achieve, naturally we have surface pressure. We're also able to determine what is the loss rate and the loss volume per stage, where each stage represents a fluid. You have stage 0, which is mud, then spacer, lead, tail, then water behind, and displacement fluid behind water. You're able to assess what is the average loss rate over each stage and how much volume have been lost or will be lost for each fluid. In addition to that, we have these black markers which represent stages, represent fluids that are pumped into the well, and we have these red markers which represent events. These events in the context of low circulation wizard are representative of when each fluid reaches the loss zone. Event 1 means that the spacer reached the loss zone, etc., etc. By having the event average stable, we're able to assess when the spacer, which is fluid 1, event 1 means that spacer fluid 1 or stage 1 reaches the loss zone, the loss rate significantly reduces and the loss volume also significantly reduces. That means that spacer, since in this case is the first fluid with LCM package in it, is able to mitigate the losses significantly. That is attained by monitoring the loss rate. You can see the loss rate significantly reduced when fluid 1 reaches the loss zone. And in addition to that, we're able to monitor how much loss rate we have and how much loss volumes we have from that point on. All these informations allow us to assess how effective or how efficient these fluids are and the fluid versus N LCM packages in the goal of mitigating losses. In addition to that, we'll get a valuable information as to how much volume of each fluid are we potentially losing or are we potentially saving as a result of the fluid LCM Taylor solution. The initial tool will be a standalone tool, which is Low Circulation Wizard 1.0, where we're going to have this stage average of stage results we already discussed, where each stage represents an individual fluid that is placed into the wellbore. We have the event average, which represent actually when each stage on each fluid reaches the loss zone and what are the actual loss rates and loss volume from that point on. In terms of actual graphical results, we're going to have real-time versus calculated pumping pressures. And we're also going to have loss zone pressures and loss rates, in addition to loss zone ECDs and the limits of pore pressures and fracture gradings. We will also have a 2D fluid position, which is going to be responsive to the losses and the loss dynamics, and ultimately will give us a more accurate representation of what the 2D fluid position or top cement output will be when losses are attained, or when losses are mitigated as a result of using a Taylor fluid and LCM package. So low circulation wizard enable us to improve our top cement prediction in cases where losses are attained by giving us the ability to model multiple loss types and add our increased and improved understanding of our loss model. And with that, we'll move to our next solution, which is CVL Visualizer. How do we optimize our top cement predictions? And what we do here is we're able to position side by side our ISEM 3D displacement prediction for top cement or fluid placement with an actual CVL. We'll be able to import a DLIS file into ISEM and having that side by side comparison. In first place, what that side by side comparison will do is will improve the reliability and the accuracy of our model. And by having that side by side comparison, you will be able to use that information in some cases to meet regulatory requirements. In addition to that, it will help us continue to push the boundaries and the limitations of the model as we get more cases, and those side-by-side comparison will be able to continue to increase the reliability and the accuracy of the prediction. The main advantage of this prediction is that we'll be able to generate an ISM predicted CVL based on displaced 3D simulations. We'll be able to position that side by side with the actual CVL determined based on that imported in this file. Ultimately, we'll continue to have our existing 3D displacement responses or graph. We'll be able to generate an ISM predicted CVL based on the displaced 3D display, based on the 3D displacement predictions or simulation results. We'll be able to generate that CVL predictive map, which will be responsive to the different displacement efficiencies. As you can see from the percentages are representative of those. It will be the main factor influencing those CVL predictive maps. And then you have that DLEASE import, which will generate an actual CVL. And having that side-by-side comparison will continue to strengthen the reliability of the model and the accuracy of the model. It will challenge the model naturally in some cases, will push us or will push the limit of and the boundaries of the model so that we continue to improve the accuracy and reliability of the same. You'll continue to have access to these displaced 3D results, but just adding that added value of giving you the opportunity to have a side-by-side comparison of the predicted CVL response that ISM displaced 3D provides versus the actual CVL, so that you can use that information to meet, in some cases, regulatory requirements. That's precisely what this CVL visualizer will enable you to do, is how do you achieve the ability to meet this regulatory requirement by having a side-by-side comparison between the prediction of the model versus the actual CVL, which ultimately will strengthen the accuracy and reliability of the model to the point that you'll be able to use the prediction in many cases to meet any type of regulatory body needs or requirements. That takes us to the last solution, which is the temperature mapping. Our ability to use or take advantage of wells where optical fiber is deployed. And by having those optical fibers deployed prior to a cementing operations, we will be able to monitor not only cementing placement, but also cementing properties or hydration while waiting on cement. Currently, all these wells, we have an interrogator at surface that's able to collect the data while waiting on cement or while placement of the cement job. The challenge or the key or the end goal of this tool is to be able to tie that information with ISM, to be able to overlap that temperature map generated by the optical fibers with the ISM calculator and predictions. That's precisely what we have here. We have a DTS data, distributed temperature sensing in degree Fahrenheit, in the left y-axis. And we have percent cement displacement efficiency, which is a prediction from ISM, in the right y-axis. And we have measured depth from 0 to 20,000 in the x-axis. So you can see here is that the initial temperature measurement from the optical fiber was collected after 14 hours of waiting on cement. After 14 hours of the initial measurement of when the fiber was deployed. Then that measurement is that red line. As time increases, what we continue to see is that there's a changing on temperatures on our specific area of the well. What we tend to look for is that inflation point, which is the shallowest depth at which that inflation point occurs. And that is representative of hydration, which is indicative of where the fluids are, or basically where cementitious-based fluids are, which are the ones that generate heat, represent an exothermic reaction, and generate heat or release heat, and as a result increase the fluid temperature. By monitoring that inflection point and overlapping that with our cement displaced 3D prediction, we're able to assess and to map where the top of cements are, and potentially provide you with this information so that you can use these as a confirmation of top cement and fluid placement. Now, ultimately, what we have here is enabling these welds where we are able to deploy a casing with optical fibers, in this case in the annulus, coupling that with our understanding of heatohydration, and the cement represents an exothermic reaction and releases heat and its temperature increases as the reaction takes place, which is what we see here is a cement with heatohydration, and the temperature measure in cases where no heatohydration is 10, you see that temperature peak. And then by having the optical fiber deploy in the cement system hydrating or over time, we're able to learn multiple pieces of information from this DTS map. And what you have here is in the y-axis, you have depth from 0 to 20,000, elapsed time from 0 to 1250, and then you have the temperature ranging from 70 degrees C to roughly 255. Going for purple in the cold temperature side and then red in the hotter temperature areas. There's several pieces of information that we can get from this map. Number one is when the cement placement took place, is when you see that variation in color, which is a variation in temperature. That change in temperature is representative of something taking place on the well. In this case, this is when the cement job is executed. And number two is very apparent and very obvious, is this sudden change in color, which is a sudden change in temperature that start taking place roughly around 780 minutes. And what that represents is heatohydration, when hydration starts taking place. In this specific case, what you note here as well is that the range of the well where hydration is taking place increases over time. And that takes place considering that the cement at the shallower positions is at a lower temperature, and as a result, hydration for those cements will take longer. But what this gives you is the ability to predict fluid position while waiting on cement. They will give you the ability to make well-informed decisions as to when to resume drilling, when to continue with operations, having an understanding of where the fluids are and where the top of the cements are. In addition to that, something else we do with this information is to take a time derivative of that temperature map. By doing that, keep in mind we have a scale in the y-axis from 0 to 20,000 feet measured depth. In the x-axis we have time, and then the color map represents what is the magnitude of the changes. Okay. These changes are representative of when temperature changes took place. And these high peaks are representative of when the highest inflection points or the highest derivative are present within the data. On the right side, this right image, what we're looking at is measured depth in the same scale from 0 to 20,000. We have distributed temperature sensing in the top x-axis from 0 to 300 Fahrenheit. And we have the predicted from ISM percent cement or displacement efficiency from 0 to 100. And then in addition to that, we have this yellow line, which represents the percent cement displacement efficiency predicted by ISM prior to execution. And then we have the initial temperature measured at roughly 14 hours. This initial temperature is while waiting on cement. This represents the reference temperature. Okay, after we continue to monitor the temperature of the well, by just monitoring the DTS measurement, you can see the hydration start taking place. And you can see that the top of cement or the hydration is indicated that you have fluid hydrating up to 16,000 after 16 hours, 12,000 after 19 hours, 11,500 after 22 hours. And what we're looking for here is that inflation point, at which point that change takes place. 11,000 after 25 hours. And we continue to look for that inflection point, at which depth that temperature starts increasing. That's 10,000 after 28 hours. And we continue monitoring, right? And over time, what you're getting is well-informed Well-informed data. You're taking actually measured data, measured temperature data that is giving you well measured data in order to assess where the fluid placement is. Ultimately, this will enable you to make well-informed decisions. It's at which point are you able to meet the top of cement objective by having an actual temperature measurement. And finally, after 37 hours, you have that inflection point roughly at 9,000 feet. When we compare that with the derivative of the temperature map, we see that that highest inflection point at that depth is where that highest inflection point is attained. When we overlap this with our ISM prediction, it further supports the ISM prediction reliability. What it suggests that 65–67% of the cement is at that specific depth. For this specific design, when we do a weight on cement test or a UCA test on that specific concentration of contamination or level of contamination, 65–67 cement spacer, we're able to actually achieve set points in those cases. Ultimately, what this is a very exciting response of the model is when we're able to overlap the model prediction with actual measured data and they align with each other. It's exactly what we're seeing here. So it's just a very exciting set of results that further support the model prediction is in alignment with actual measurements. And this actual measurement being overlapped or coupled with our model prediction is going to give you the ability to assess fluid placement while waiting on cement. Not only that, but it will give you the ability to determine when to continue or to resume operations based on this information. It will also give you the ability, also importantly, to provide this actual measurement of fluid placement to meet regulatory requirements. I mean, essentially, you're determining where your fluids are. And this is a point to assess whether you really need a CBL at this stage or not, because you're going to have an actual prediction that aligns with your actual measurement, and you'll have a predicted CBL from the ISM prediction, and you have an actual measurement of hydration, very indicative of where your fluid placement is. And this is information that you can naturally use to meet regulatory requirements of where fluid placement is and where your top of cements are. Ultimately, what we're able to achieve with temperature mapping is give you a very powerful tool that will couple ISM predictions with actual temperature measurements, taking advantage of our understanding of hydration to assess fluid placement and ultimately top of cement so that you can meet the regulatory requirements. It is potentially minimizing the need or replacing CBL requirements, since you're able to get an actual measurement and you're able to couple that with our displacement 3D prediction and our CBL prediction. And by having the prediction and the actual measuring in complete alignment, you'll be able to support that information and to provide that measurement as a fluid placement requirement, or the ability to meet the fluid placement requirement. So today I have introduced you to iTOC, a remarkable initiative that encompasses 6 great solutions. Real-time validation, which gives you the ability to monitor job placement and expected downhole ECDs while execution is taking place. Real-time advisor, which provides you with the capability to forecast job placement while the job is being executed, and most importantly, it can give you the opportunity to adjust placement parameters in an attempt to meet job requirements in order to achieve top of cement. SEMLive represents a cloud interface that will enable you to access real-time job execution and historical job results. Loss circulation wizard, which merges our optimized understanding of the impact of multiple loss types in induced and natural fractures along with permeable formations, and what is the impact of those losses on the hydraulic response of the wellbore, and ultimately what is the impact of losses on top of cement. The CVL visualizer will enable you to compare side by side the accuracy of our 3D displacement model in relationship to the actual CVL, and it will also serve as an opportunity for us to continue to challenge the boundaries of our predictions. And most importantly, it will serve you as a top cement confirmation for regulatory purposes. And lastly, the temperature mapping, which allows for monitoring of cement hydration while waiting on cement, thus enabling for straddle replacement and top cement assessment. This gives you the ability to measure fluid placement and measure top cement potentially even prior to meeting or to achieving wait on cement time recommendations. As a result, you can yield savings to your operations and an ability to provide measured fluid tops to meet regulatory requirements without the need in some cases of CVL, since you have an actual measurement of fluid placement. In essence, iTOC will enable a digital engineer and a digital operator to remotely access a rig location, which can now enable a specific SME also access to any required operations, regardless of the SME's location. All of these will enable for the end goal that we all want to achieve, which is instantaneous job validation. An ultimate objective in instantaneous job validation that is not possible without your collaboration as our clients and our ability to continue to listen and respond to your needs. None of this, and let me be clear, none of this will be possible without your collaboration, without the help and the need and your communications in regards to giving us the opportunity to continue to work and collaborate with you in order to engineer different solutions. And as a result, we would like to encourage you to please participate in this Voice of Customers and continue to provide your feedback so that we can collaborate and engineer solutions to maximize the value of your assets. Thank you for your time. If you have any questions, feel free to reach out to me as well.